Hi, hello everyone. Welcome to another workshop session with Magnimind. I'm very happy to see you guys here. I would like to share my LinkedIn account first. So if you guys want to connect, you can connect. Feel free to connect, please. And second, I'm going to share with you the file that we're going to use. There is not much actually, but there is one data file and an empty Jupyter notebook. So you can use that. If you don't have Anaconda, if you don't have Jupyter notebook installed, you can use Google Colab. So it's very easy to use Google Colab. So I can show you very shortly how you can use Google Colab. So what are we gonna do today? So if you participated in any of the workshops that I did with Magnimind before, so the assumption was that we didn't have too much of knowledge on Python or machine learning. Today, I mean, if you don't know Python, it's going to be a little bit difficult, but you can still walk through the code with us. But it helps if you are familiar with Python. Okay, then for today's workshop. So what are we going to do in this series of workshops? We are going to actually get into details of these very basic, as Dr. Badai said, very basic models, algorithms that we are using in machine learning. The first one is linear regression. If we apply to big companies as a data scientist, you might receive a question on these fundamentals of these algorithms, and also it's going to help you sharpen your coding skills. It's not a very big deal in terms of coding, but still, as a data scientist, if you know how to code the basics of how to code an algorithm from scratch, it's going to help you a lot. You can understand the inner wirings of the algorithm. Okay, so to try what we are doing, actually, my suggestion is if you want to learn or develop the algorithm from scratch, I always prefer working on a paper. So take your pen or pencil and then just write on the paper. So, but today we are not just going to write or type, but we also want to run whatever we are building. So in an interview, people are not going to ask you to run. People are not going to expect the code that you are writing is going to be what's that, executable. But in this workshop, what we are going to type or write as code, we expect that it's going to be executed without any errors. So for this exercise, we are going to use this housing data set. There are so many housing data sets available. So the housing data set, I got this, it's a public data set, and also some of the pieces of code that I'm going to be using, it's coming from Sebastian Rochka's machine learning textbook, machine learning book, actually, machine learning and PyTorch, deep learning with PyTorch. It's a fantastic book, actually. I really recommend if you guys are looking for a book to learn machine learning from, I recommend that book. One of the books that I recommend. So we are going to use Ames housing data set. I just shared the Google document with you, so you must have access to this file, Ames housing txt, and also linear regression scratch class. As I said, it's an empty notebook. So this is the explanation. This is just the description of the columns in our data set. We're not going to use all of them. We're just going to use one of the columns. Again, this is just for the purpose of testing whatever we are writing as the code, whether it's going to be running smoothly or not. So now let's run this cell here, and it's going to. And by the way, whenever you have questions, please feel free to post them to the chat. So I'm going to be following the chat. So let me move this aside so I can see. Can see the questions. Yeah, so housing data set is right here, guys. So I just shared the Google document with you. Okay. All right, so let's run this. Organize this place here. So sorry about that. I'm trying to see what you're typing. Okay. All right. So now, whenever you are working with trying to run linear regression, I mean, if you go and check any textbook, listen to any YouTube tutorial, so we are going to say, oh, you can use scikit-learn linear regression, right? So linear regression class from scikit-learn. So scikit-learn is an open source library, which is a fantastic library full of all these algorithms available for us. And linear regression is one of them. So you can use it. And I didn't share the screen. Okay. I thought I was sharing the screen. I'm sorry, guys. Yeah, okay. I hope you guys can see the screen now. So yeah, linear regression, you can just run this from scikit-learn. So all the estimators with scikit-learn, and this is not just specific to scikit-learn, but I suggest stick to one library and then learn that library. It's gonna be helpful. If you go and check what kind of methods, so when you instantiate an instance from linear regression, let's say linear regression. Okay, let's say you instantiated LR from linear regression class. So LR comes with certain methods. So, and all the estimators at scikit-learn will come with these three methods. Okay, LR dot, what is that? LR dot say fit. Okay, so this is the first method. The second one is going to be, of course, when you fit, you're gonna put the data and the label. And then you're going to have predict. So this is going to be predicting given data. So capital X is representing the feature set and Y is the labels. And the third one is score. Again, this time you're going to put X and Y. So first you're going to predict labels for X, which is going to give you Y hat. And then you're going to get the score for Y hat given Y. So you are testing how well your model is doing, right? So you're comparing Y hat with Y. For linear regression, the score, I mean, we might have different scores. So we are going to be using in this class R squared, in this session R squared. So what we are going to do is we are going to create a class which is going to have these three methods, three functions. Okay, so we are going to create this. Okay, so before getting into developing the code, let's remember what linear regression was about very briefly in a couple of minutes. Yeah, Harold, I didn't import anything. This is just for the illustration. So let me also type the import thing. So again, yeah, linear model. I always from scikit-learn model, right? So import. So this is how we import. This is how we import linear regression and then instantiate and then run. Okay, so let's remember what linear regression is about. Why? Because we need to know the variables that we are going to be using. So this is going to help us to write the code, right? So what is linear regression? We have X, which is the feature set. Okay, so let's think about X. What is X? What is capital X? So again, depends on how you define X, you're gonna write the code, right? So let me say X is rows of the X observations. So each row is going to be an observation. It can be a person. In our data set, it's gonna be a house. Okay, and then columns will be features. So in this case, in our case, columns will be overall quality, overall condition, the living area, the square footage of living area, whether it has central air or not, and total basement square footage. So these are the columns of our data set. So again, X rows are observations, columns are features. And we are going to also have Y. So Y is our label. So in this case, Y is going to be, so again, it depends on how you are going to define. So Y is going to be a a vector, right? It's going to be a vector, and it's going to be a column vector. Okay, it's going to be a column vector. So it's going to be a tall column vector. And what is y in this case? In our case, it is the sales price, sale price. So this is the target variable. Okay. All right. So what I'm going to do is, the way linear regression works is, I'm going to have one coefficient for each feature. I'm going to have one coefficient for each feature, and I'm going to multiply that feature with its corresponding coefficient and then add it up. So basically, my y hat, which is my prediction, let me also note this, y hat is my prediction. Okay, y is the ground truth value, y hat is the prediction. So y hat is going to be, right, equal to coefficients times features and then sum them up. So it is the weighted summation of features. One thing that we also need to note in here, we have the bias term. Okay, so we also have some bias term, which is nothing but y-intercept of a linear line. Okay, so in most of the textbooks and then in practice, what we do is, instead of having a separate bias term, we just add one column of all the ones into our X matrix. Okay, but in this case today, I'm going to treat bias term as one separate vector. Capitalization means, the capital letter X means it's a matrix. So it has rows and columns, right? But Y is just a vector. So that's why I'm using small y, okay? X, again, if you write it small x, it's okay. Nobody is going to question why you are writing x as small. But by convention in mathematics, when we want to express a matrix, we are using capital X, or capital letters, okay? Okay, so what is y hat? So y hat is going to be at W0. W0 is going to be the coefficient of the bias term. Again, what is bias term? In this case, it is 1. Okay, so let's make this 1. Okay, so W0 is the bias term itself. It's the coefficient for bias term. All right. Plus W1 is going to be the coefficient of the first feature. And W2 will be the coefficient of the second feature. And let's say I have P number of features, P number of them. And then observations, let's say I have N number of them, N. Okay, so then this is going to be WP times XP. By the way, this is the first time I'm teaching linear regression from scratch. So I hope things will go smoothly, okay? All right, so Y hat is W0 times 1 plus W1 times X1. So now we can write this equation as multiplication of as of now, Y hat is only for one data point. Let's call it I. Okay, then X1 is going to be the ith data set, the data point. X2 is going to be the second feature of the ith data point. XP is going to be the pth feature of the ith data point. What is ith data point? It's one of the houses. Okay, among all the houses in my data set, I pick one house, that is house I. Okay, house I, right? For house I, I'm writing my prediction, price prediction for house I. But then I have many houses. I have n number of houses, n number of houses. So that's why X is a matrix. One row from X is ith house or jth house or kth house. Okay, but capital X is all the houses. Yeah, I think this is going to be recorded. So then let's write this more general. So Y hat is X, again, depends on how you define. Be careful. Okay, so I defined X as rows and columns. So X times and then I said Y is a column vector. So X times a W transpose. And what is W? W is a row vector of W0, W1, W2, W3, WP. Okay, so I'm taking the transpose of W so that it's going to be a column vector. Then the first row of X times that column vector, W transpose, it's going to be my prediction for the first house. Then second row, inner product of second row with the column vector W transpose, it's going to be my prediction for the second house and third house and nth house. Okay, so this is how I'm going to be making my prediction. Okay, so if this part is clear in our minds, now let's motivate how we are going to. So our goal with linear regression is finding W's. We don't know W's at this point. Our goal with linear regression is finding W's, which is going to make our prediction as close as possible to the ground truth variable Y. Again, Y, known prices, ground truth label, okay? And Y hat, predictions. So we want to bring our predictions as close as possible to the true values. So then our model is going to be successful. Okay. Then what I'm going to do is I'm going to define error, okay, which is Y hat minus Y. Okay. And then I'm going to say, because sometimes this error is going to be negative, sometimes positive. Let me make it positive by taking the square root of this. So then I'm going to say that squared error, let me use SE, is Y hat minus Y squared. Okay. And then let me take the average of this squared error, mean squared error. It is going to be, what is that? 1 over n. Okay. And then summation of Y hat I minus Y I squared. Okay, so far we just used the definition, the variables that we already defined. Y hat I is my prediction for ith house. Yi is the true price of the ith house. I'm taking the difference of these guys, the difference of my prediction and the ground truth, taking the square root of that because I don't want negative and positive numbers for different houses cancel each other. And then I'm summing them up across all houses and then dividing it by number of houses. This is my mean squared error. Next, I want to find, remember, Y hat is, let me also write this way. Y hat is, I'm writing instead of Y hat, I'm writing what Y hat is. It is Xi times W transpose. Okay, so I just used this equation here. Instead of capital X, I'm using Xi. Xi is the row for the ith house. Okay, so this is mean squared error. Now what I'm gonna do is I'm trying to find the W that is going to minimize this error. So this is my error, total error. I want to minimize this. How can I minimize this? So what I'm going to do is I'm going to take the derivative of this mean squared error. Take the derivative of MSE with respect to W. Okay. So that is going to be called in literature gradient. Okay. So I'm just taking the derivative of mean squared error with respect to W, which is going to give me the gradient. So what is gradient? Gradient is going to, again, if you think your mean squared error as a curve, okay, which is starting from some high value and then going down and making a minimum and then going up again. Okay, imagine your mean squared error is can you draw this graph? I'll try to draw it. Normally I was using my iPad to Well, but let's see. Let's see. Something like this. Okay, can you see it? Okay, so this is your mean squared error. Okay, let's say this is your mean squared error. So on the x-axis, you have W. Okay, so you're looking for a W, this which is going to give you this minimum point. Again, what is the y-axis? Mean squared error. Okay, so you're looking for, yeah, mean squared error. You're looking for W, which is going to give you the minimum error. Okay, so the gradient, it's actually going to tell you, with respect to W, whether you are climbing or whether you are going down the hill. Okay, so if your gradient is greater than 0, then you are climbing. That means you are running away from the minimum. Okay, if your gradient is less than 0, okay, and that means you are actually going down the hill. Okay, let's say you are here. Let's say you are here. Let me change the color. Let me be cool. Okay, so let's say you are here. All right, let's say you are here. So at this point, wow, you have some W. Okay, here W at this point. Sorry guys, W prime. All right, you're right here, and your gradient is less than 0. You take the derivative of your mean squared error with respect to W, and then it turns out to be negative. That means you are here. So what you have to do is, if your gradient is negative, that means you are on the left of the minimum point. Then you need to increase your W. You need to increase your W so that you can get closer to the minimum point. So how are you going to increase? You are going to increase your W in steps, okay, until you feel like, you know what, I got enough close to the minimum. I'm going to stop. So you're going to do this in terms of number of iterations. Okay, if your gradient is greater than 0, let's say you are here, that means you are here, you are climbing, that means you are on the right hand side of the minimum. In that case, you need to decrease your W, right, so that you can get closer to the minimum. Again, these, I'm going to call this step size. Let's call this learning rate. Learning rate. Okay, so I'm going to now erase this whole thing, all right? Okay, so we got the idea about what this gradient business is doing. So that if gradient is if gradient is, sorry guys, is negative, we are on the right hand side of the minimum of MSA, then I'm sorry, on the left hand side of the left hand side. So we are, if gradient is negative, we are going down the hill. Then increase your W. So if gradient is positive, we are on the right hand side of the minimum of MSA, then decrease your W. As you see, what I'm doing is I'm taking the opposite sign of, if it is negative, increase, if it is positive, decrease. I'm taking the negative sign of my gradient. Okay, so again, this is going to help us to understand when we are typing the code. All right. Now let's take the derivative of this term here. Let's take the derivative of this term here with respect to W. It's going to be gradient will be, look, 2 over n. Okay, I'm taking the derivative of this term. I'm taking the derivative of this term with respect to W. It's going to be 2 over n xw minus y times x, right? So square term is coming to the left hand side as 2. I have one xw minus yi, and then take the derivative of xw minus y with respect to w, it's going to be x. So this is my gradient. So I can write this gradient as 2 over n times, remember what xw, this guy, remember what this guy is? This guy is y hat. Remember what y hat, so let me write it explicitly here, y hat minus y times x. Remember what y hat minus y is? Error, right? 2 over n error times x. So this is my gradient, okay? Once I get my gradient, okay, once I get my gradient, what I'm going to do is I'm going to take my w, the current w, and then I'm going to take negative of gradient, okay? But remember the step size. So what I'm going to do is I'm going to multiply this gradient with some step size eta. Okay, if eta is big, you're taking big steps. If eta is small, you're taking small steps. So depending on the sign of the gradients, either you are increasing w or decreasing. You are just taking the opposite. You are just going to the opposite direction with your going to the opposite direction of your gradient. Okay, so I just tried to give you beforehand what we are going to write the code for. So that's why I spent some time with this one. All right, now let's get back to the beginning, at the very beginning. We said we need to have fit, predict, and score. All right, so we are ready to, eta is the step size. Yes, eta is the step size. Now we are ready to write the code. Okay, so let's write the code together. So what I'm going to do is I'm going to create a class. Okay, so let's call this class. So again, remember with Python, those who are new into Python, we have functions to reduce redundancy in the code. And we have class to reduce that redundancy even further, to put functions which are related to each other together. Okay, that is why we have class. Well, there are some other reasons, but basically in this case, that's why we are going to be using class. We are going to put related functions like fit, predict, and score together inside one class. So let's name our class as linear regression and then stochastic descent. Okay, so this whole process is called stochastic descent gradient. Okay, so this is our class. Our class will have functions. Let's call this, let's first write the names of the functions. So I'm going to have one function, let's call it fit. Okay, I'm going to have another function, let's call it, what is that? Predict. Okay, I'm going to have another function, let's call it score. All right, so I'm going to fill in these functions, but for any class, before even starting with these three functions, I need to define my construct, right? So I need to talk about the instance that I'm going to create from this class. For that, I'm going to be using this built-in function init. So those who are new into this class business, you might be puzzled with what is in it now. So this guy, whenever you create an instance from class, give me just 1 minute to explain what class is in this case. Okay, let's say you have a student class. Okay, you create a class like student. So this student take course. Okay, register, take exam, register course. Okay, and I don't know, student can do other things too. So student is the name of the class, and then all the students in the university or in that institution are actually an instance from this class. Each individual student is an instance from this class. So whenever I say student 1, whenever I say this, I'm creating an instance from student class. Okay, so this init function is going to give some initial attributes to the student. For example, the student should have a name, should have a phone number, should have an email, should have a student ID. So all these attributes will be the initial attributes that are going to be assigned automatically whenever you create an instance from student class. So that's why we are using this init function. All right. So this init function has the first parameter always self. Self will be referring to this guy here. Okay, the instance that we are creating. My question is how to use linear regression analysis in real life situations. Let's get to it if you like later, because it's a different story. So for linear regression, we are using it to predict for continuous variables, continuous labels, actually, target variables. Okay, so whenever I create one instance for my linear regression, I need to assign a value for eta. Let's assign an initial value for this 0.01. You can 0.01. You can change this later on. You can assign different values to eta, and then I'm going to repeat this procedure, this gradient procedure. Remember, we were going to be step by step. So that is going to be number of iterations. So let's say number of iterations is 50. Again, you can change number of iterations too. And then let's also assign a random state of 1 so that whoever runs this class, they are going to have the same random variables assigned. Okay. Again, eta is the step size. When you are taking the gradient and trying to approach to the minimum W value, eta is going to tell you how fast you are getting to that W. It's going to be your step size, learning rate. So if eta is big, then you are going to be taking big steps towards W minimum W. And the danger is if eta is big, you may jump over the minimum and get to the other side. Remember the curve I drew earlier? So yeah, the if learning rate is big, you may jump over the minimum. Okay, so this is initial function. So let's assign our variables. Again, self is referring to the instance that we create from this or instantiate from this class. So self eta is this eta value. So this eta is 0.01. Eta is self eta is the attribute of that self. Okay, so let's continue. Self dot number of iterations is number of iterations, and self dot what else? Random state is random state. Again, on the right hand side of the equations, I am defining. I'm already assigning the arguments, parameter values. On the left hand side, these are the variables these are the attributes of self. Self is referring to an instance. Whenever I call this linear regression, whenever I do this, okay, later on, I'm gonna do this. And then let's say this is my first linear regression, okay? And then I can call this one more time. This is second one. So it's almost like this is one student, this is another student. So these are two separate instances. I just created two separate instances, all right? So both of these instances have their own etas, number of iterations, and random state variables assigned. Okay, again, self is referring to the instance that I just created. Okay, so this is a standard built-in function that we have to define anytime we are creating a class. Again, this init function will be different from one class to another. Okay, so now let's work on fit. When you fit, again, if you go back to scikit-learn, right? Linear regression, scikit-learn's linear regression. Remember, when you fit, what you need is the data set and its label. So these are the parameters of the fit function. In this case, fit method. So we are going to say always when you are defining a function inside a class, the first parameter is self, all right? And then X and Y. Again, X is our data set, Y is the label. All right. Now, bulk of the code will be here. Okay, bulk of the code will be here. So please bear with me. All right. So this part is going to be the core part of the coding. Once we are done with fit, everything will be very simple. So what are we doing with fitting? First of all, let me tell you what we have to do. Okay, what we have to do. Remember here, I am going to step by step update my W. I'm going to be updating my W step by step. What is that step? I'm going to take, at each step, I'm going to take the gradient, check the sign of the gradient. Depending on the sign of the gradient, I'm going to take a step at the size of eta. And then I'm going to repeat this for some number of iterations. All right. Okay. So this is an iterative process until I'm out of number of iterations. Okay, I exhausted number of iterations, I'm gonna stop. But I have to start from somewhere. So I have to assign some initial value to W. So I'm searching for the best W value, but I have to start from somewhere. I have to assign an initial value to W. If you assign 0 to W, it's going to be, so I'm not gonna get into it, but it's not going to be a good practice, assigning initial values of 0. So wherever you start as initial value for W is going to tell you how long it's going to affect how long it's going to take for you to get to minimum. All right. So I need to assign some initial value to W. The best way to do that is assign some random numbers to W. Okay, random numbers. So for that, I'm going to use Numpy's random package. np.random. Using numpy.random, you can use scipy random, library too. So it's up to you. But numpy's random. From numpy's random, I'm going to instantiate one instance from numpy's random. Okay, with some random state. So why I'm using this random state? If we are going to be running this code, we want to have the same random numbers generated. Okay, that's why I'm using the same, so it's random state. So if you change random state, you're going to be assigning different random numbers. So this is going to be self random state. What is the self random state? It is already assigned in here. What is self? Self is the instance that I created, and right now I'm defining that instance. These are the attributes of that instance. This is the method of that instance. So this function also comes with LR1. This function comes with LR2. Okay, so let's call this random number generator. Okay, and then this random number generator, I'm going to be using normal distribution with some mean value and standard deviation. All right, so this is mean, this is standard deviation. Again, these are, when you are in an interview, maybe these may not be so important. Okay, so when I say these two lines, but because we are going to run the code, so I'm trying to be careful so that the code is going to run smoothly. Maybe you don't need to be in this detail when you are writing this on a board. Comma. Scale. So this is, I'm generating a random variable, normally distributed random variable with 0 mean and 0.01 standard deviation. And how many random numbers I'm generating? The size of this, so I'm generating an array of random numbers. So the size will be the number of observations in my data set. So shape, number of columns in my data set, right? Because W is as many as I'm going to have as many W's as number of features. Okay. All right. So I am going to be now assigning these random numbers to my initial, to my what is that? To my weights. Okay, that's what I'm gonna do. So what I'm gonna do is this guy will be equal to W's of my instance. Okay, again, I assigned some initial values to W's. Again, these W's are W1, W2, WP. I didn't do anything for W0. Okay, I'm gonna do it now. All right, and then let's call this W0. Okay, and this will be equal to 0. Okay, so for bias terms in general practice, we can assign 0 values. For bias terms, we don't care really about that. Okay, all right. So I just assigned some initial values to my W's and W0. This is the bias term, remember. Okay. All right. Now, what I'm going to do is I'm going to create a for loop for I in range of number of iterations, right? Self number of iterations. So what is number of iterations? I just defined it here. So I'm going to be running this loop for 50 times in this case. I can change it later, but I'm going to be updating my W 50 times. That's what it means. All right. So let's now find our Y hat. Remember what Y hat was? Y hat was, let's see, our predictions. So what is our predictions? X times W. Okay, X times W. So that's what I'm going to use. Y hat is, I'm going to use the following, the dot production from Numpy. Okay, all right. So it's going to be X multiplied by W, okay, which is self W, this guy. Okay, and then what else? I'm going to also add self W0. So I'm simply using the definition here, guys. Y hat is W0 plus W1 times X1 plus W2 times X2. I'm just using this definition here. Okay. All right. So I got my Y hat. Later on, I'm going to replace this Y hat with a function. Okay, but let's not worry about it now. Okay. Now I need to find the errors. Error is nothing but Y hat minus Y. I already defined that here. Error is Y hat minus Y. This is my error in my prediction. Next, gradients. I already defined gradient here. Okay, I'm going to use this one here. Okay, let's use it. Gradients is 2 times, okay, 2 times X. Now I'm going to take the transpose of X. I know what I am doing, but so let me write mathematically. X transpose times W is the same with X times W transpose. Okay, X transpose times W is the same thing with X times W transpose. Okay, so earlier when I was describing Y hat, it was equal to X times W transpose. Now I'm using this one. Okay, it's the same thing. So 2 times X transpose. Transpose means you take a matrix, you hold the matrix from lower left and upper right and flip it. So what you do is actually you are taking all the, you are making all the rows as columns and columns as rows. Okay. Oh, I'm just making it as a float number. That's why I added 0 here, 0 dot here. Okay. I just made this as a float number. If I just put 0, it's going to be integer. Okay, X transpose, then dot product of errors. So I'm doing this, guys. I know as we move forward, it's becoming more complicated, but just keep in track. Okay, so I just explained the steps that we are doing. So it's not easy. I know that it's not easy if you are this the first time or second time you are looking at this, but I mean, you have to do this at some point if you really want to learn the details of the linear regression. Okay, so I'm doing this one here. This one, look, this one here. Okay, I already explained this one. Error times x, so that's what I'm doing here. X times errors, and then 2 divided by n. So what is n? N is nothing but the number of rows in my x. So x dot shape gives you number of rows and number of columns. Actually, it's a tuple of number of rows and number of columns. Sebastian, so the name of the book that I was suggesting was Sebastian, I forgot his last name, Rochka. Okay, so this is gradients. All right, so this is the gradients. Next, I'm also going to do the gradients of the bias term. Okay, bias gradients. Again, it's the same thing, but for bias term, this x is equal to 1. This x is equal to 1. So that's why I'm going to write bias term as a separate gradient. So I'm just going to copy this. Okay, I'm just going to copy this here. But again, for the bias term, x is 1. Okay, x is 1. So that's why when I take the derivative of with respect to w, I don't have any x. All right, I don't have any x. So x is 1. So what I'm going to do is I'm going to simply, instead of this, 2 times errors mean. Okay, I'm just taking the mean of the errors. Okay, why I did this one? Let me explain this, guys. Y hat is W0 plus W1 times X1 plus W2 times X2, blah, blah, right? So if you take the derivative of Y hat, with respect to W, okay? So let's call this del Y hat W, all right? Then you see that this first term, it's 1. The second term, it's x1. The third term, it's x2. So derivative of the bias term is 1. So there is no x term in here. That's why I don't have any x term for the bias gradient. Okay, del derivative. So when we say the sign for derivatives, we call it del. So that's why I call it del. It's derivative. So let me write it derivative. Okay, for the gradients bias term, we don't have any x because we don't have any x. This is W0 times 1. Okay, so when you take derivative of W0 with respect to W0, you only have 1. And then you are taking derivative across all the users, I from 1 to n. What you are having is summation of the error terms. 1 times error 1, 1 times error 2, 1 times error 3. You are summing them up and dividing by number of data points. That's why bias gradient is errors.mean. It's the mean of the errors. Okay, so we got the gradients. Now I need to update my W's. Okay, I'm updating my W. Look, this is how I started. Now I took the derivative of W. Now I'm updating my W. So this is my old W. This is my old former W, which is at this point here. I'm going to take the negative of gradient. Remember, negative of gradient. If gradient is positive, I'm going to decrease my W. If gradient is negative, I'm going to increase my W. Eta times gradients. All right? So eta is the step size. Similarly, I'm going to update my W0. Let me also put this underscore here. So these underscores indicate that these W's or W0s are generated inside the class. Okay, W0 is self.W0. Okay, not self. Minus eta times bias. Okay, not bias. So I updated my W as well as my W0. All right, I updated my W as well as my W0. So let me also keep track of my errors. Remember, my loss is the squared of error. So this is error can be negative or positive. I'm going to take the squared of that. This is the squared. All right. So again, error is a vector. It's a vector. So error has my error for the first house, my error for the second house, my error for the third house. This error is a vector of size n. What is n? N is the number of my data points. So I'm going to take the mean of this. So this loss is my average loss, average mistake, average error on my predictions, okay, across all my data points. Well, if you want to keep track of your loss, how your loss is decreasing as you iterate over, as you update your W. So for that, let's create an empty list to keep track of my loss. So let me call it what? Self losses. So this is an empty list. So what I'm going to do is self losses. I'm appending this loss. Okay, so what I'm doing is every time I find loss for the first iteration, I put inside this list. I find loss for the second iteration, I put into this list. I find loss for the third iteration, I put. So this list is keeping track of how my loss is changing as I iterate through W's, as I update my W's. Okay. Errors. Yes, thank you. So I missed the S in the errors. Thank you. Okay, let me make this. All right, guys, we are almost done with this one. So again, as I said, this is the most, what is that? Complicated one. And then let's return self. So whatever we assign to self in here, all W's, W0s, losses, okay, they will all be returned from this function. When we run this function, we are going to have losses, we're going to have W0, we're going to have W. So anything that is attributed to self will be returned. Okay. How my loss is changing as I iterate or update my W's? Again, when you change your loss, so that this loss will tell you how your loss is going to change. Okay, guys. So we are done with the most difficult part. Okay, the rest will be much simpler. All right. So remember here, what we did here was, where is it? Let me see. This one, right? This one is actually prediction, right? This is prediction. Look, so I'm just what is that? Multiplying X with W and then adding W0, right? So let's use this predict. So for prediction, what I need is self always, because it's a function inside the class, and then X. So what is prediction? Let me just copy this. Okay, I just copied it. All right. So prediction is X times W plus W0. I already gave you here. Y hat is predictions, and Y hat is nothing but X times W. Of course, plus W0. Let's call it plus W0 so that you know that this also includes bias term. Okay, so I got my prediction. Then maybe I can change this to a function, right? Instead of writing it this way, I can change it to a function, right? Self dot predict. What I'm going to do is x, right? So then it's going to run this function here. All right. Okay, so this is prediction. Now let me also write score. So when I predict, I'm going to also test my okay, so I'm going to test my algorithm. Okay, so score. For score, what do we need? First of all, we need self. I need my data set and I need my true labels. Okay, I need these X and Y to test score. So what is the score? What are we going to use for score for linear regression? I will be using, where is it? I'll be using R squared. I put it somewhere, I think. Okay, anyways, let me write it here. For score, I will use R squared. Now let's think, what is R squared? Okay, what is R squared? R squared, if you check the literature, is nothing but 1 minus, look guys, 1 minus. So what you're gonna do is you're going to find your error, 1 minus summation of errors, okay, divided by summation of y minus y bar squared, okay? This error, let me write it explicitly, y minus y hat squared. Of course, squared is also inside the summation. Okay, now let me explain what this y bar is. Y bar is nothing but average of labels. In other words, y bar is summation of y divided by length of y. Okay, that is y bar. Y bar is the average price. If this is the house prices, y bar is the average price. Okay, so what is y hat? It is your prediction. So what you are doing here is actually, you are looking at your prediction, how much error you are making here. And what if your prediction was your average? Okay, what if your prediction was the average? So this is your error with respect to if your prediction was the average. So if your prediction is totally equal to y, okay, that means your prediction is 100% successful, your R squared is going to be 1. If your prediction is worse than the average price, then your R squared is going to be negative according to this definition. Okay, all right. So again, if your prediction is equal to y, that means you are predicting the price perfectly, your R squared will be 1 because y minus y hat will be 0. If your prediction is the average price, y minus y bar divided by y minus y bar, this whole thing will be 1. 1 minus 1 will be 0. Then your R squared will be 0. That means if your prediction is the average house price, your R squared is 0. If your R squared is negative, then your prediction is even worse than the average price. Then there is no point in running that algorithm, right? So if your prediction is worse than average price, anybody can tell that, oh, what is the prediction for this house? Let's use average price. Anybody can say that. So that's the baseline model that you can use, very simple baseline model. Okay, so let's now use this to write the code. Okay, so we need to, first of all, find y hat. How can we find y hat? It's right here, self dot predict x. Right? This is y hat. Okay, I found y hat. Next, I need to find the y bar. Okay, let's find it. Y bar is nothing but take the mean of y. Okay, all right. Next, let me find the errors. Error is, I already did that before, right? But let's do it again. Y minus y hat. Okay. Next, I'm going to find, let's say, this guy. Okay, this guy. So let's call it sum of squared of residuals. So errors are also called residuals. Let me put a note here. Errors are also called residuals. I'm using the word RES so that you know in the literature they are also called residuals. Otherwise, errors or residuals are the same thing. Okay, it is nothing but errors squared. Okay, errors squared, and then add them up. First, take the squared and then add them up. Okay, right here. Summation of, where is it? Yeah, summation of this squared. Okay, I'm gonna do the same thing for, let's call it sum squared of total. This time I'm gonna be using y bar. Okay, so y minus y bar squared. Okay, and then take the sum of this. Okay, so I found the total sum of squareds. Next, I'm gonna define my r squared. R squared is 1 minus residual over total. Okay, residual over total. So this is, sorry, this is residual over SS total. Okay, I got my score, r squared. Let's find one bonus score. Okay, let's also find root mean squared error. Okay, root mean squared error. So first of all, let's find mean squared error, which we already found earlier. It is nothing but this guy divided by the length of y, right? It's the average of the errors. And then root mean squared error is nothing but MSE. You can do this to the power of 1 over 2. Okay, it is a square root of MSE. Okay, you're almost there, guys. Now return RMSE and R squared. Sum of squared of residuals, SSRES. Sum of squared of residuals. What is residual? Error terms are also called residuals. So it's another word for error terms. So I could, if you are confused with this, I can call it error. Okay. Okay, I think we are done. That's it. So predict y hat NP dot. Let me see. Predict NP dot. So yeah, this is okay. This one is okay. Should remain to self dot predict. Where are you referring to? I didn't get it. Some of NP y hat is, yeah, should remain or change to y hat. No. So you are referring to, this is predict, and this is the function itself. Okay, this is the function itself, predict function. Okay, so let's try if we did everything correctly. So error squared, hold on, it already gave an error. Error squared, where is it? Loss. Okay, so let us try if we did correctly everything. Okay, let's try. So we already imported the data set df. So what I'm gonna do is I'm going to take the what is that? X. Okay, I'm gonna say X is, I'm just going to take one column of df. So which column? Let's use this column, guys. This one. Okay, let's use this one. Just to make it simpler, okay? All right. And then y is, again, df. Let's use this one. Okay. And then let's turn them into series. Okay. Let's see. So let's see X. It's an array of living space area. And then let's also check Y. And this is the price corresponding to these houses. Okay. Do you have return in predict? Let's see. Yeah, of course. Let's return this one. Yeah, thank you. Or let's do this. Return Y hat. It's going to be more readable. Okay, thank you. Okay, so this is X and this is Y. Now I'm going to show you one thing, which is going to be. Let's see. First, let me try something, and then we might see an error, and then I'm going to explain why we are having that error. Okay, if you are ready now, let's take one instance from linear regression SD. Okay, I'm just going to copy this. By the way, I said it was going to take 40 minutes, but we are over one hour. I'm going to stop soon, okay? Okay, you see, I just created one instance from linear regression SD. Next, I want to fit. Again, the moment I say dot fit, I'm referring to this guy here. Okay, fit X and Y. Let's see what it's going to say. Okay, it said tuple index out of range. So somewhere we made some mistake. So then we need to fix it. Let's see. I'm going to fix it very quickly. Normal, the size is X shape 1. So it's giving the error here. Self W. Okay, and random state self W. Size is X dot shape. Nice. I see. So I need to make this two-dimensional array because I'm using shape. So I need to make this two-dimensional array. Okay. Okay. Now what? So it has W0. We made a mistake here. W0 is here. W0 is here. W0 is here. So where is that mistake here? Y hat self predict, Y hat MD, self W0. I see. This one, right? Okay. Now what? Eta is not defined. Eta, self eta, eta. Where is it? This one, right? So eta is not defined because we are going to use self.eta, right? I'm referring to eta from the self. Okay. Okay. So this is what I meant. This is one mistake error that I was expecting. So overflow encountered in square loss. So because this price is really high, this price number is really high. So when we take the square root of the errors, we are generating a really long number. And that is beyond the size of the number that we are going to be using with Python. So that's why we are getting this error. So if you had tried this for smaller numbers, we wouldn't have any problem. So to fix this, let me do the following, okay, very quickly. And that will be also a practice for you to use scalar, standard scalar from scikit-learn. So I'm just going to scale my data set, that's all. And you can do this manually too, but let's do this very quickly. So what I'm going to do is I'm going to take my data and then I'm just going to scale it, okay? So my data here, a standard scaler is, let me call standard scaler twice. Standard scaler for X. And standard scaler for Y. I'm just making the numbers bringing the numbers into the range of 0 and 1. That's all, okay? With standard scaler, because when I work with big numbers, I'm getting this error. I don't want to get that error. I can fix it, but that's beyond the scope. So we don't want to deal with that now. Okay, X is X dot fit transform X. I'm going to do the same thing for Y. Sy dot fit transform Y. Standard. I see. So these are all the errors that you are going to encounter, guys. So no worries. Scikit-learn expects all it for its estimators and transformers two-dimensional data. Right now, Y is here, X is, let's see. Here, X is two-dimensional, Y is single dimension. Okay, so that's why I'm getting an error with Y. So what I'm going to do is I'm just going to add a new dimension to Y. That's all. And it's very simple. I'm not doing anything with Y. I'm just adding one new dimension to Y. So this one. Okay. So, and then I'm again going to flatten it. So I'm going to explain what it means. Let me first take care of this. New axis, Numpy, new axis. It's still be I. Yeah. All right. So let me explain what happened here. As you see, Y is a single dimensional and X is two-dimensional. So all scikit-learn estimators and transformers expect two-dimensional data. That's why we are having this error. So what I did is here, let me tell you this, Y shape. I'm almost done, all right? Just bear with me for a couple of more minutes. You see, so this is my Y. I'm not changing anything with Y. I'm just adding one dimension to my data set. That's all. Now it is two-dimensional. Okay, I didn't change my data. Now I'm going to take this guy. Look what I'm doing now. I'm turning it back into, again, single dimension. Okay, flatten. Flatten takes two-dimensional data and turns it into single dimension. Here, look, X two-dimensional, Y is single dimension. I'm adding dimension to Y. Now it becomes two-dimensional. Now that two-dimensional data, I'm again flattening it and then turning into one dimension. Okay. All right, almost done, guys. So I'm going to use this. I just used that. What is it? Here. Now Y is transformed and they are small. Let's see how they look like. Look, X 1 to 10. What is it? X ST 1 to 10. All right. Look at the numbers. So I just scaled them, brought them into a range of -1 and 1. Basically, what I did is I took the mean of X, subtracted it from X, and divided that subtracted number by standard deviation of X. Okay, let's now do this. Okay, so I fit my data. So let me also take the score, okay, LR.score X ST ST. And it gave me an R squared because I made a mistake here, R squared. See, the mistake that we are making is coming after us. Okay, I got it. All right, so it works. Before we leave, let's also test this with regular linear regression. Okay, test this with regular linear regression just to see that it is working. Okay, so from scikit-learn linear model, regression. Okay, then LR scikit-learn is regression. And then LRS.fit, what is that? X is T, Y is T, LRS.score is T. So this is the score. It's almost this. It's almost close. The score is a little bit different because the way we maybe generated the score was slightly different than what scikit-learn did. Let's test it this way. Let's test it this way. So let's check the coefficients. So this is the coefficient, and for the bias term, this is the intercept. Okay, so this is the coefficient for scikit-learn, and this is the bias term. Let's also check our LR. LR dot, what is that? W0. Let's go this way. Here, right? Okay. But W is a little bit different. Let me see. We made a small mistake at some place. Check it very quick. Okay, so there's a very small mistake. Let me fix it and then share the file with you. I don't want to take your time, but this is how we are going to generate linear regression from scratch. There is one tiny mistake that I cannot see it now. I'm going to fix it, and then I'm going to put this file into that folder so you can have access to this file as well. Okay, so let me stop here. Thank you so much. I'm going to have another session tomorrow for logistic regression. All right, and hopefully the next day, like KNN, and then the next day, K-means clustering. Again, this was the first time I did this live, so any mistakes, sorry about that. We'll see. I'm gonna see you guys tomorrow. Bye. Take care, guys.